In this video, I'm going to go through the OCR Chemistry A-level paper. That's paper 2 and June 2018. So that's the synthesis and analytical techniques. They call it paper 2. Okay, right. Well, a straightforward knowledge question. Which compound is used as the standard for NMR chemical shift measurements? Of course, is tetramethylsilane, that one. These three are all used as solvents in 1H or in NMR spectroscopy because they don't. The D is 2H. They don't contain any 1H, which would make the give their own spectrum. Okay, which compound is a secondary amide? So we're looking for an amide, which is this group, and the secondary amide where one of the hydrogens is replaced by an alkyl group. So the answer is that one there, is C. Okay, A is an amine. Likewise, B is an amine, and D would be counted as a tertiary amide. Which compound does not react with nucleophiles? Well, the aldehyde would do, because you've got a delta positive on there. This one wouldn't. There's no partial charge on a carbon. There's partial charge on a carbon there, partial charge on that carbon attached to the chlorine. Okay. Which structure represents an alicyclic compound? So an aliphatic cyclic compound, so it can't contain benzene ring. So the only one that it could be is this one here. The others all contain, well, a delocalized electron structure. Okay, which molecule is not planar? Right, so ethene is. You've got trigonal planar because you've got 3 groups around the carbon, no lone pairs. This one is, again, 3 groups, no lone pairs. D is actually linear, but that's all fits on the same plane, so it's planar. And of course, this one, you've got tetrahedral carbons in there, carbons bonded to 4 different things, and so that is not going to be planar. Bond angle is 109.5. The number of peaks in the 1H NMR spectrum of that compound. So to avoid making mistakes, it's always a good idea to sort of to draw these out and number the carbon atoms. 1, 2, 3, 4, 5. It's 5 long. You've got a carboxylic acid on each end, and you've got an OH attached to carbon number 3. Okay, so these are going to be hydrogens. So that gives us quite a bit of symmetry there. So we're going to get 1 peak, those two are the same. That CH2 is the same as that CH2, so that's 2 peaks. The hydroxide hydrogen is unique, that's 3. And finally, that one is unique, so that's going to be 4 peaks is the answer. Ethanol can be prepared by different reactions. Which reactions? So the lowest atom economy. Right, first of all, it's not going to be that one because that's 100% atom economy because you only make ethanol. Right, now, to do this quickly, we look at the weight of the other compound produced. So HBr is pretty heavy. That's 79, that's 80. Ethanol is 46. So that one is going to be, yeah, right, that one is this one, okay. This one you're making 46 and a 60 for the ethanoic acid. This one you're making 2 times 46 is 92 and 80, 2 times 44, 88 for the carbon dioxide. So they're all about 50%, except this one here is lower. Okay. Okay, now question 8. The breakdown of ozone is catalyzed by NO radicals. This is you need to know the mechanism, and you need to know that that one is the propagation step. Okay, infrared spectrum. Which compound could produce the infrared spectrum below? Right, so we forget about all of that stuff there because that's the fingerprint region. This is very characteristic of an alcohol OH, even without looking at the thing there. You get the alcohol OH, and it's always next to, you always get the CH peak there. So just check the alcohol, 3,200. It's not broad enough for a carboxylic acid. And then this very distinctive sharp peak here, 2,200, that can only be the nitrile. So we're looking for an alcohol and a nitrile in the same molecule. It's that one. Okay. Really, you could do that just on the nitrile, really. Okay. Because that's so distinctive. It's the only one with a nitrile in it. Okay. Benzene reacts with an organic reagent in the presence of a halogen carrier to form phenylethanone. Right, so what we've got to do here is we've got to stick on that group. So that is going to be the electrophile. How do we generate that electrophile? Well, we generate it by removing the chlorine from that compound with the halogen carrier, aluminium chloride usually. So that's gonna take off that chlorine with the electrons to make that. So the answer is the acyl chloride, which is C. Question 11. Right. How many straight chain isomers C7H15Cl contain a chiral carbon? Well, if you look at that, that's like C7H16. If you count the chlorine, it's like a hydrogen. So that's saturated. No double bonds to worry about. We've got 7 carbons in a row. It's only the straight chain ones. Right. So where can we put the chlorine? Okay, let's put it on the end. And you can see that that carbon, if it was on the end, that carbon would not be chiral because it's got 2 hydrogens attached to it. You've got 4 different groups for it to be chiral. Right, so really, in order for it to have a chiral carbon, we've got to stick a chlorine on because anything with 2 hydrogens, obviously, they're the same. So that position there, no, you can't get a chiral carbon. Let's see, if you stick the chlorine here, yes, you will get a chiral carbon because that carbon is going to have the methyl group, the hydrogen, the chlorine, and then this big group here. Right, now that's the same if you put the chlorine there. So that's just 1. Now let's see if we put the chlorine on this carbon atom there. Would that be chiral? Yes, it would, because you're going to have ethyl group, hydrogen, and butyl group, and chlorine. And of course, that's exactly the same if you put the chlorine there. So we've got 2 isomers so far. Let's see, can we get a third one with a chiral carbon? Well, if you put the chlorine there, you can see it's not going to be chiral because you're going to have a propyl group there and a propyl group there. So they're going to be the same. So you've only got 2. So B is the answer. Right, mass spectrum of this compound is shown below. Which ion is responsible for the peak with the greatest intensity? Well, the greatest intensity, that's at MZ of 43. Now, if you check the MZ of all of those alternatives, they all are 43. So we have to think so that's not going to help very much. Okay, so let's draw this out. So we're going to have 2 methyls there, hydrogen there, and then we're going to have okay, right, now can we get this fragment? That's a possibility if we get rid of that and that's what fragment we've got there. So that's got a fragment twice, so maybe not, and that's not maybe the best alternative. That is impossible because we haven't got that thing in the molecule there. This is impossible because we haven't got a carbonyl compound carbon there. So that is going to be the one. C is the answer there. It only needs to fragment once there, doesn't it? Just there to give you C. Okay, which statements support the delocalized model for benzene? Okay. All carbons have the same bond length. That is true, yeah, because they're not really like that, are they? Alternate single double, they're all the same length. That if it was like that, you would expect to have, if it was really double bonds and single bonds, you'd have short, long, alternating. The enthalpy change of hydrogenation is less than expected. That also supports the idea. I think that gives you, you'd expect it to give you 3 times minus 120. That's what you get when you hydrogenate one double bond, which is equal to minus 360, and you don't get as much as that. I think you get minus 208 or something. You don't need to remember those numbers, obviously, but that's what it is. So that's right. And bromine reacts less readily with benzene. That's true as well. Bromine doesn't react with benzene because benzene does not undergo addition reactions, which alkenes do, and that's because you've got delocalization, which makes it less favorable to break. It's less energetically less favorable than breaking a double bond. So all 3, 1, 2, and 3. So A is the answer there. Okay, 14, a question about recrystallization. Right, with recrystallization, you want to dissolve your compound in the minimum volume of hot solvent. Okay, and then when you cool it down, the crystals are going to come out, crystals form. Okay, and that's because it's a lot more soluble when hot than cold. So let's just check. So that's the principle of recrystallization. Let's check it. The organic compound is more soluble in hot solvent. Yes, we want that. The hot solution is cooled before the, yeah, we do cool it to make the crystals form. The 1 and 2, right. Now this one is wrong. The melting point, if it's impure, the purified is, the melting point of the purified compound is lower. Now, when you have impurities, that makes the melting point lower, slightly lower. It's slightly, so like when you put salt into water, it makes it impure, lowers the melting point below freezing. So 1 and 2 is the correct answer there. Yeah, so if you test the melting point of your compound and say it should be 133, and you get like 131, there's a probability that you've got impurities in there. It's depressed the melting point. Okay, which of the following could react with the compound below to form a carbon-carbon bond? Right, so let's see. Now this, so that would, aluminium chloride is a halogen carrier. It will generate that electrophile from chloromethane, and that can react with the benzene ring. Okay, so that can. KCN in ethanol, right, yeah, that will work because we've got a delta positive on that carbon, and CN minus is going to react with that. So that's right. This, now methanol and sulfuric acid, that's going to make an ester linkage here. And an ester linkage, of course, doesn't have you don't form a new carbon-carbon double bond, you form a new carbon-oxygen bond. So that's not right. So it's 1 and 2 for that. Okay, organic, so this multiple choice section is finished now. Organic compound containing carbon, hydrogen, and oxygen. A chemist investigates the reactions of this alcohol A. Systematic name of the alcohol. Okay, so I'm going to number the carbons and number it from this end, so the alcohol is on the shortest, got the smallest number. Okay, so we can see it's butanol, but we've got a methyl group on carbon number 3, so it's 3-methyl, should be a hyphen there really, methyl butanol. It would be wrong to number it the other way around. If you numbered it like that way around, 1, 2, 3, 4, and called it 2-methyl butanol, that would be wrong because you should give the ol the smallest number because that's the functional group. Okay, so the chemist heats, I've drawn a picture of alcohol A again here because it's going to react with an acid catalyst to form a mixture of 2 alkenes. Draw the structures of the 2 alkenes. Okay, so we're going to dehydration with the acid catalyst, and we're going to remove the OH and a carbon from the hydrogen next door. Now let's say if it removes it from the blue carbon there, we've got a hydrogen there. you are going to get this product. Sorry about that. You are going to get this product, right? So the skeleton is the same, and we have formed a double bond between those two carbons. If you remove it from this carbon next door, the red one, then you are going to get a different, the double bond in a different place. You're going to get it there. Okay, so they're the two alkenes you can form there. Right, the chemist heats alcohol A with sodium chloride and sulfuric acid. Now, when you do that, the sulfuric acid is a catalyst, and the chloride ion acts as a nucleophile, and you're going to get nucleophilic substitution, and you're going to swap that for a Cl minus, so you're going to get OH minus. So a balanced equation. Okay, show the structures of the organic compounds. So I'll do CH3, CH3, H, OH, CH3. Okay, and we're going to react that with, I'm going to react to the Cl minus sign. They're quite happy with you to do, ionic equations. And what's going to happen there is you're going to just swap the, so that's going to be Cl, and that's going to be H, and that's going to be CH3, and you're going to get OH minus coming off. But if you left it like that, you'd get it wrong, because you've got an acid catalyst in there. Okay, so there's no way you're going to make OH minus in the presence of an acid. That's going to react with H plus to form water. So we should put down here plus H plus, and that is going to go to H2O. That is, in my opinion, that's the best way of writing that equation. You are allowed to put in the spectator ions as well, but I think that's much simpler to just write it like that. Okay, and it's that you'll find the mark scheme accepts that. Okay, right. B is a triol, and it's refluxed with excess potassium dichromate to form a single organic product. So, of course, dichromate is going to oxidize primary alcohols to a carboxylic acid. A secondary alcohol, it's going to oxidize it to a ketone. And tertiary, of course, it doesn't touch. Now, let's see what we've got here. We've got, this is a tertiary, so that's not going to be oxidized. This one's going to go to a ketone. And here we've got that's a secondary, and we've got that one there is going to be oxidized to an acid. So let's draw the product there. We're going to get CH3. That doesn't change. That turns into a ketone, and that turns into a carboxylic acid. Okay, so I need to now count up, see how many hydrogens I've lost. Okay, so how many hydrogens I've lost? Okay, let's see. Well, I've lost that one and that one, that's 2. And I've lost those 2. So that is 4 hydrogens, so that's going to be 2 H2O on this side. Then I need to see how many oxygens I've got. Well, on the left, I've got 3 oxygens. And on the right, I've got 1, 2, 3, 4, 5, 6 oxygens. So that means you gain 3 oxygens, so I need to put a 3 there to balance it. So that's it. So it's 3O in the square brackets, and you get 2 waters as well. And you get a ketone and a carboxylic acid. Right, okay, so we've got this compound C, and we've got to draw the organic product of these reactions. So compound C has got a carboxylic acid on each end, and it's got a carbon-carbon double bond, an alkene group there. Okay, so let's see how steam and phosphoric acid. right? That is going to react with an alkene group. If you remember what happens when you react an alkene with steam, and the phosphoric acid is a catalyst, you end up sticking an OH onto one carbon and an H onto the other one, so you turn it into an alcohol. Now, these two carbons are the same because this molecule is symmetrical, so it doesn't matter which one the OH goes to, you're just going to get one product. So the product is going to be, I'll draw it outside the box because it's too small. That's going to be CH2, that's going to be the alcohol, and that's going to be the carboxylic acid. That's the product you're going to get. Okay, it doesn't matter whether it sticks on that carbon or the other one because it's symmetrical. Right, this one, excess methanol and sulfuric acid. Well, methanol in the presence of a sulfuric acid catalyst will react with the carboxylic acid groups to form an ester. So you're going to get a diester. So I'll do that in blue up here. You're going to get CH3O at that end. You're going to have your double bond still. That's not going to be affected. And the other carboxylic acid is also going to be an ester. You're going to get that there. And then you can polymerize this. Well, what kind of polymerization can this undergo? I know it's got a carboxylic acid. You may be thinking ester, but you haven't got any alcohol there. So it's going to be an addition polymer with the carbon-carbon double bond. And remember, when you form addition polymer, so what we've essentially got there, I'll do it here, is you've got a carboxylic acid group there and one there. Well, so you get another molecule next door to it, exactly the same. You're going to break the double bond there, and you're going to form a new bond to the one next door. So that is the repeating unit. Okay, onto amino acids and optical isomerism. Okay, so the amino acid cysteine has got this R group, and it shows optical isomerism. Draw 3D diagrams to show the optical isomers of cysteine. Well, first of all, let's just draw our general structure of amino acid. We have this carbon here, which is attached to a carboxylic acid group, a hydrogen, the R group, and the amino group. And of course, it is this carbon which is always asymmetric, except in the case where that R is hydrogen. So what we got, so we've got cysteine here. So that R group is going to be CH2SH. So we'll just draw there's our asymmetric carbon. We've got one group coming towards us, one going into the plane of the paper. That one sticking up is in the plane. That one is in the plane. So let's put H, the amino group. Let's put the R group. And this is going to be the carboxylic acid group. Right, and imagine our imaginary mirror there. We're going to draw the mirror image of that for the optical isomer. So it's, remember, they are non-superimposable mirror images of each other. So you've got the NH, we've got this, sorry, got the carboxylic acid group there. You've got the R group coming out, the NH2 group going in, and that there. So those two, if you try and superimpose them, you made a little model, you won't be able to. That's what they are. That's the two isomers. Right, lysine has got this group, okay, and with an excessive dilute hydrochloric acid, it will form a salt, okay. So we're going to react with HCl. Right, we're going to protonate this nitrogen here, and we're also going to protonate the other nitrogen in the other amino group. So let's draw lysine. First of all, we've got, here's our general carboxylic acid. Here's our NH2 and lysine CH2. And it's going to be 4 long, and we've got the NH2 there. Right, so with hydrochloric acid, well, hydrochloric acid is not going to touch the carboxylic acid group. It's already protonated, but it will protonate this one. So make that 3 with a plus charge on it. And this is going to be 3 as well with a plus charge there. Now it does ask us for the salt, so we can't really just show the positive ion. We have to draw the two chloride ions in this. So you're going to, that chloride is going to be a chloride to go with that one and a chloride to go with that one. Okay. Okay, alpha amino acids, which are naturally occurring amino acids, can react to form proteins. A short section of a protein chain is shown below. A student hydrolyzes a protein with NaOH. Draw the structures of the organic products formed from this section of protein. Now, we just remember how we form a peptide linkage. So you've got a carboxylic acid of 1, and you've got the amino acid group of the next amino acid. So that's the end of it. And what happens is you're going to lose water there, lose that there, and we're going to form that. Okay, so when you hydrolyze that, you're going to, with OH minus, you're going to reform the carboxylic acid, but it won't be a carboxylic acid because you've got loads of OH minus about, which is a base, so it's going to be the salt of the carboxylic acid, and you're going to get NH2. Right, now where are the peptide linkages there? We've got one there, and that's all we've got. There's just one peptide shown in that. So let's draw that. Okay, so I just have to draw, let's recopy that. So it's going to be HOCH2, CH. And that's carrying on, presumably the rest of the chain. And here we're going to have, this is the carboxylic acid end. So that's going to be the ion, the negative ion, because it's sodium hydroxide. And then we're going to have the NH2 from the other bit. It's going to be CH, CH2, CH2, and the amide group at the end that they've got there. And we need to just finish that off. Okay. There are your two products. You split the protein into two. Okay. Right, question 18. Okay, phenol undergoes nitration more readily than benzene. So phenol with OH on the benzene ring. A student carries out nitration of phenol. Of course, phenol is that, isn't it? Sticks an NO2 group on it, replaces one of the hydrogens to produce 2-nitrophenol and 4-dinitrophenol and a little bit of 3-dinitrophenol. The student thought that 13C spectroscopy could be used to distinguish them. Explain whether the student is correct. Right, now we need to have a look at how many different carbon environments we've got in each of these. So let's have a look at 2-nitrophenol. Oh, we've got 1 carbon environment there. That's unique. There's none others like that. 2 there. Now that one is, number 3 is unique because it's next door to the NO2 without, 4 is unique, 5 is unique, 6, they're all unique. So that's going to give you 6 peaks. Let's look at 3-dinitro, right? You've got 1 peak there. That's unique. That one is unique between the OH and the NO2. That one's obviously unique, and yet you can see 4, 5, and 6. They're all unique, so there's no symmetry in that. Okay, but if we look at this one here, we can see that that one, that's going to give you 6 peaks as well, of course. That one and that one are the same. Sorry, they're not the same. What am I talking about? Right? That one is unique, but that one and that one are the same. And you can see that probably that one and that one are the same. And then that one is unique. So that is going to give you 1, 2, 3, 4 peaks. So can you distinguish them all by NMR? No, you can't. You can say which one's the 4-nitrophenol, but you cannot distinguish between 2-nitro and 3-nitro because they're both going to give you 6 peaks. Right, why is phenol nitrated more readily than benzene? For 3 marks. So what do we need to say here? Okay, well, nitration, we're going to say occurs by electrophilic substitution, and the electrophile is the NO2 plus. Now, right, it's going to react faster with phenol because in phenol, the lone pair on the oxygen is partially delocalized. That increases the electron density on the benzene ring, which makes it easier for electrophiles to react with it. So that's your 3 marks there. Right. Now, methyl benzene reacts with sulfur trioxide to form D. Right, we've got that before. And the electrophile in this reaction is SO3, and we've got to complete the mechanism. So we need to know our electrophilic substitution mechanism here. Right. So, right, we've got this sulfur. That's the electrophilic part of the molecule because it's got a partial positive charge. So what's going to happen is a pair of electrons from the benzene ring is going to come onto the sulfur. Sulfur only will form 6 bonds, so that too many. So one of these pi bonds has got to break, and it's going to go onto that oxygen at the end. You know, to make a negative charge on it there. Okay, so the intermediate is going to look like this. Now we normally draw the H on there, don't we? And then you've got, that's our intermediate. The benzene ring, the delocalized system has been partly broken, and it's going to have a positive charge on that ring there. Okay, so that's the intermediate, and the final step of the mechanism, of course, is going to be for the pair of electrons in the hydrogen to the carbon there. That goes back into the benzene ring to regenerate the benzene ring to give us this, and the hydrogen comes off as H+. Okay, so that is that mechanism. About the hydrolysis of haloalkanes now. Okay, the rate of hydrolysis depends on the halogen present. State and explain how the halogen affects the rate of hydrolysis. Okay, so we've got to know here that when you have the iodoalkanes are going to react fastest, and then the bromoalkane, and slowest is the chloroalkane. Right, so one for the order, and now one to explain is because the bond strength, the carbon halogen bond strength increases. For 2 marks, that's all you need to say there. I don't think you need to explain that it's a nucleophilic substitution reaction and the water's a nucleophile and so on in the hydrolysis because it's only 2 marks. You just need to say that. Right, okay, so second part of this, more nucleophilic substitution. Chlorocyclohexane is hydrolyzed with sodium hydroxide. Outline the mechanism for this reaction. Okay, show curly arrows and relevant dipoles. Well, I'm going to put a dipole on that carbon has got a partial positive charge because it's attached to the electronegative chlorine. You're going to get your OH minus ion from the sodium hydroxide. The sodium is just a spectator ion, of course. That lone pair is going to form a bond pair to that carbon, and the pair of electrons in this bond is going to come off onto the chlorine, and the products are going to be, you're going to get cyclohexanol, and you're going to get a chloride ion, and that will be with NaCl because you've got Na plus is a spectator ion there. Okay, right. A student hydrolyzes haloalkane E. Okay, so they get 0.01 mole of E, and they react it with excess sodium hydroxide to give F. Right, now also what's going to happen there is you're going to get your halide ion coming off. I'll just write X minus because we don't know if it's chloride, bromide, or iodide. Okay, and then they neutralize with nitric acid to get rid of the OH minus, and you add silver nitrate, and what's going to happen there is the silver nitrate, silver ions, and the halide ion will form a precipitate of the silver halide, depending whichever one it is. They all form precipitates. Right, now, and that is G. Okay, now if we look at this equation here, they tell us we've got 0.01 mole of E, So that is going to give us 0.01 mole of F, and importantly 0.01 mole of AgX. Okay, and now that should enable us to identify which halogen is in AgX, because we've got the mass of it, 1.88. So we know, let's say moles equal to mass over mR. We want to find out the mR of AgX. So mR, rearrange it, is mass over moles. The mass we have got is 1.88 grams, and the moles we've got, we know it's 0.01. So that is going to give us an MR of 188. Right, so which silver halide is that? Well, silver is 107. Chlorine is 35.5. So 107 plus 35 is not silver chloride. Bromine is 79.9, and that's it, isn't it? 79.9 plus 107 gives you 108. So it is silver bromide is G. Okay, so we've identified G. That's AgBr. Now we can identify, let's do what E and F are. All right, so F has got a molar mass of 74 gram per mole. Okay, now so we can be able to, and we know F is an alcohol. Sorry, F is, yeah, F is the alcohol. Okay, and it's got a chiral carbon as well, it tells us. Okay, so let's see which alcohol that could be. Right, so could it be methanol, way too small? Ethanol, that's 46, it couldn't be that. Propanol is too small, C3H8OH, but yeah, C4H10O. So an alcohol with 4 carbons in it, that could be it. So we know it's 4 carbons, that's 74. MR is 74, and it's got a chiral carbon in it. So I think what we're looking at is F is going to have the OH on that carbon, on number 2, butanol. Right, it obviously can't be butanol. If it was butanol, it wouldn't be chiral. And let's just check any of the branch things don't work out. So we could have, you know, let's see, we could have a branch chain. We could have the OH there. Well, if it was there, that would have 2 hydrogens on it there, so that wouldn't be chiral. So that's not right. Or we could put the OH on that carbon, and then you've got 3 methyl groups, so that wouldn't be chiral. So the answer has got to be butanol. Yeah. For G. Now G, sorry, that's F. So if F is butanol, that means if F is butanol, that's F there. The haloalkane it was formed for, and we know it's the bromo now. There's got to be 2 bromo butane. Okay, right, let's have a look at the last question. Is that, I think that is question 20. That is the last question I'm going to do on that, and the rest of that paper will be covered in the next video.